everyone. Welcome to the third lecture on matrix method of structural analysis. What we have been doing is we have been revisiting some of the basic concept in structural analysis that you already had in previous semester. Last class we discussed what is indeterminate structure, what is determinate structure. When see at the end of the day we have to solve certain equations, right? And if that equations, number of equations available from equilibrium equation, if that equilibrium equations are not enough, not sufficient to solve completely the entire structure, then we say the structure is indeterminate structure. Now what we are going to do today is we are going to see how that indeterminacy or indeterminacy of a structure is quantified, what are the different kinds of indeterminacy we can have, and how to determine those indeterminacy for different kinds of structure. Okay. So, today's topic is static and kinematic indeterminacy. Okay. Now, you see the static degree of static indeterminacy, if you recall from your structural analysis 1, the degree of static indeterminacy is total number of unknown. That unknown could be external unknown, it could be internal unknown. We are just going to see what is external unknown and what is internal unknown. These are the total number of unknowns, and then we have number of independent equilibrium equation. You see, it is very important, it is just not equilibrium equation, it is independent equilibrium equation. On the third week you will be having a brief review on matrix method, on matrix theory, and there it will be discussed what does it mean by independent equation. Okay. So, number of equations should be independent, and then this is called degree of static indeterminacy. Let us see through some example. If you for instance, there are some beams here given, if you have to find out the static indeterminacy of the structure. Now, for instance, consider the first case, the it is a propped cantilever beam. Now, if I draw the free body diagram of the beam, the free body diagram will be free body diagram of the beam will be this. This is a fixed support. So, we have three reactions here, and this is AX, AY, this is AX, and this is MA, and this is roller support. We have one reaction, that is BY. So, number of unknown is 4, 1, 2, 3, 4. So, number of unknown 4, and then how many equations are available? We have 3 equilibrium equations, summation of Fx is equal to 0, summation of Mx is equal to 0, and summation of Fy is equal to 0. These are the 3 equation we have. So, the degree of indeterminacy, static indeterminacy is 4 minus 3 is equal to 1. Okay. Now, if we take the second case, the second one, the free body diagram if I draw, then again you have 3 reactions here, and then we have, it is a hinge support. So, again we have 2 reactions here. Let us use different color. We have 2 reactions here, one is this and another one this, and we have another 2 reactions here, one is this, another one is this. So, we have total unknown is 1, 2, 3, 4, 5, 6, 7. So, number of unknown is 7 and number of equations available is 3. So, total static indeterminacy becomes 4, right. Similarly, if we take this example here, this is here we have 2 reactions, these are 2 reactions, and then you have one reactions at the roller support, another reactions at the roller support, one more reactions at the roller support. So, total reactions are 1, 2, 3, 4, 5. There are 5 unknowns and the number of equations available is 3. So, 5 minus 3 is equal to 2. So, in this case the static indeterminacy is 2. Now, consider the last example. You see, if we draw the free body diagram of this is 2 reactions here because it is hinge support, we have a roller support, another reaction, another roller support, and then another roller support, another reaction, and then in addition to that we have one hinge here. Okay. So, how many equations are available? We have 1, 2, 3, 4, 5. There are 5 unknowns and the equations are available. Equilibrium equations available is 3. And then in addition to that, since it is hinge cannot take any moment. So, additional equation available at the point of hinge, that moment at this point is equal to 0. So, total number of equations available is 4 and total unknowns are 5. So, 5 minus 4, that is, so in this case the degree of static indeterminacy is 1. Now, you see in this case the degree of, why it is called external? Because somehow if we determine the support reaction, suppose for the first case, these support reactions are somehow, if we can calculate these 3 support reactions, then at any point we can determine what is the bending moment, shear force and axial force. So, internal forces can be determined easily if we know the support reactions. So, the indeterminacy here is we cannot determine the support reaction based on the equilibrium equation. Now, if we remove one support reactions, then the structure becomes indeterminate and we can calculate the support reaction. So, here the indeterminacy is due to the additional number of supports which is not required for stability of the structure, and that is the reason why this indeterminacy is called external indeterminacy. Okay. Now, if we see one more, if we see the frame structure, you see here this, if we draw the free body diagram of the entire structure, this is the free body diagram, and then we have this is one force, this is hinge support, 2 forces, and this is roller support, we have 1 more forces. So, here support reactions are 3, 1, 2 and 3, and the equilibrium equations available is 3. So, in this case the external, there is no indeterminacy due to the support, additional support provided in the structure. So, in this case external indeterminacy, external static indeterminacy is 0. But you see, when we say that we have to analyze the structure, it is not just the support reaction, we have to find out the member forces as well. Now, let us see, we have just now seen this is externally, it is determinate structure, means we can calculate the support reactions. Now, if we know the support reaction, can we calculate all the member forces in this structure? If we can, then the structure is internally determinate as well. But if we cannot calculate the member forces, even with the knowledge of support reactions, then the structure is called internally indeterminate. Okay. Now, for instance, now let us see this structure. Now, suppose now we know what is the support reactions, right? Now, suppose take the free body diagram of AB. If we draw the free body diagram of AB, then free body diagram is like this. We have 2 reactions, AX and AY, and since this is a rigid frame, then at any point we have 3 forces, axial force, shear force and moment. These are 3 forces. Now, for this AX and AY, these 2 are known, because we have already, AX is known and AY is known, because we have already calculated the support reaction, because it is not externally indeterminate. So, these 2 values are known. Now, if these 2 values are known, then in this free body diagram only unknown are M, F and V. Then we have 3 equations, summation of Fx is equal to 0 and summation of Fy is equal to 0 and summation of M is equal to 0 at any point. So, this gives us V is equal to Ax, V is equal to Ax. This gives us, say, F is equal to Ay, and similarly this gives us M is equal to 0. So, for this, as far as AB segment is concerned, so we can determine these 3 forces. Okay. But again, as I said, it is when we say the structure is determinate, it means at every member we can calculate the member forces. Now, let us see whether for other members as well we can determine the internal forces or not. Consider now this joint B. if we take joint B, then the free body diagram of joint B becomes this. We have three forces here, three forces here, and again another three forces and another three forces. Now, from this you see already these are known, M, F, V are known, right. What is this one? This one is actually, if I draw the, it is for member AB, this is for member AB. So, this gives you MBA. So, MBA is known, MBA is known, this is known, then F is known, F in BA is known, and then shear force in BA, that is also known. So, these three are known. Now, in this free body diagram, total unknown are, here it is 3, here it is 3, and here it is 3. Total 9 unknowns, and out of these 9 unknowns, 3 unknowns are already known from the free body diagram of AB. Now, but still we are left with 6 unknowns. We have 3 equilibrium equations, and with these 3 equilibrium equation, we cannot determine these 3 unknown. So, indeterminacy for this structure is 3, right. Now, you try to compare this example with the previous example. In the previous example, the indeterminacy is caused due to the additional support, and that is why the indeterminacy was called external indeterminacy. In this case, the indeterminacy externally the structure is indeterminate, but the indeterminacy is due to the additional member of the structure, right. So, therefore, that member force we cannot determine with the knowledge of, with the information of equilibrium only, and that is the reason why this indeterminacy is called internal indeterminacy. When we say the indeterminacy of a structure, it is total indeterminacy, external indeterminacy plus internal indeterminacy. Okay. Now, let us say if you recall from your structural analysis 1, that if this is the internal indeterminacy of this rigid frame can be obtained by a formula 3C, when C is the number of closed loop. For instance, this here it is one closed loop. This loop is not closed. So, here C is equal to for this example C is equal to 1. So, internal indeterminacy is 3 into C, means is 3. Okay. Now, take a few more example. For instance, if we apply the same concept here, in this case what is the external indeterminacy? You see here we have 2 forces, here also we have 2 forces, and here also we have 2 forces. So, there are total 6 unknown, and we have only 3 equilibrium equations. So, internal indeterminacy of this is external indeterminacy is 6 minus 3 is equal to 3. And what about internal indeterminacy? Say C is equal to 1, we have 1 closed loop here, we have 2 closed loop here. So, total closed loop is C is equal to 2. So, indeterminacy is C 3C, it is internal indeterminacy which is equal to 6. So, total indeterminacy is 6 plus 3, total indeterminacy is 9. So, for this indeterminacy is 9. Take one more example. So, in this case, here it is also same example. So, your external indeterminacy will still remain same. External indeterminacy is 3, and internal indeterminacy we have just one closed loop. So, internal indeterminacy is 3C, which is equal to 3. So, total indeterminacy is 6. 3 plus 3, total indeterminacy is 6. Okay. So, this is static indeterminacy. Now, these are all for frame structure, beam and frame structure. And what about for truss problem? If you remember, the truss problem was for truss problem. Okay. For truss problem sake, first consider the free body diagram of this truss. If we take the free body diagram of this, the free body diagram is this. And we have two support reactions here, we have one support reactions here. Okay. Now, suppose R is equal to suppose R is equal to total number of reactions required. For instance, in this, as far as this truss is concerned, R is equal to 3, 1, 2 at this point, and at joint E it is 1. So, total 3. And suppose in this truss, how many members we have? 1, 2, 3, 4, 5, 6 and 7. Suppose M is equal to total number of members. Now, then total number of unknown becomes what? R is the support reaction. So, R many support reactions we have to determine, and then in truss all members are the 2 force member. Therefore, the internal forces we have only one, which is the axial force in the truss member, and therefore, the internal forces, number of internal forces is same as the number of members. So, total unknown here is M plus R. Right. Now, how many equations we have available? Now, if we take the free body diagram of any joint, say for instance joint B, if I have to draw the free body diagram. So, free body diagram of joint B will be something like this, and this is FBD, this is FBC if you recall, and this is FBA, this is joint B. Now, here we do not have three equilibrium equation, because the truss we cannot have truss member, all the joints are connected through pins. So, there is no moment resistance. So, only resistance we have in translation, I mean x and y translation. So, only the equilibrium equations available here is summation of Fx, summation of Fx is equal to 0 and summation of Fy is equal to 0. So, this is the only two equation we have available at every joints. So, if you have total number of joint is j, total number of joint is j. So, total number of equations available at each joint is 2 equations. So, total number of equations available is 2j. So, this is the number of unknowns, and this is the number of equations available. So, we say that the structure is determinate if this 2j is equal to M plus R, and if say the structure is indeterminate if M plus R is greater than 2j, right. Now, therefore, for truss we have the following. If the number of, this is R is the number of reactions, total reactions, M is the number of member, 2j is the number of total equations available. Then we have 3 cases very similar to the depending on whether M plus R is less than, equal to or greater than 2j. If M plus R is less than 2j, means your structure is your number of unknowns is less than the number of equations available, the structure becomes unstable, and when this is exactly the same, the structure becomes stable and statically indeterminate. Now, I would like to emphasize this point stable here. You have just put a star marks here, and then again if the M plus R is greater than 2j, we say the structure is indeterminate, again put a star mark here, stable. You see, these conditions, say M plus R is equal to 2j or M plus R greater than 2j, these conditions are necessary condition for a structure to be stable, and or the structure to be determinate or indeterminate. But these conditions are not sufficient condition. Just based on this condition, we cannot comment, or we should not comment on the stability of the structure. The stability of the structure is something that you have to at this point you have to physically verify, look at the different orientations of the member, look at the joints, and then see by whether the structure, the entire configuration, the assembly is stable or unstable. Just to make it in a proper perspective, let me give you 2 examples. For instance, this example. Okay, so this just now. Before that, before we give you the example, let us say few examples to calculate the static indeterminacy of structure of truss member. Now, you say here number of joints j is equal to 1, 2, 3, 4 and 5. So, number of joint is 5. Number of members M is equal to 1, 2, 3, 4, 5, 6, 7. This is 7, and number of support reactions, we have 2 support reactions here, we have 1 support reaction at E. So, R is equal to 3. So, total number of is equal to 10, total number of unknown is equal to 10, and number of equations available is 2j, which is 10. So, statical indeterminacy is 10 minus 10, which is equal to 0. So, this truss is statically determinate, right. Now, let us take one more example. Now, here also if you see your number of member M is equal to 1, 2, 3, 4, 5, 6 and then 7, 8, 9, 10, 11, 12, 13. So, number of member is 13 and then number of joints is here 2, here it is 1, number of support reactions R is equal to 3, so total number of unknown is 16 and then number of joints we have is 1, 2, 3, 4, 5, 6, 7, 8. So, number of joint is equal to 8. So, number of equations available 2j is equal to 16. So, static indeterminacy is 0. So, structure is statically determinate structure. So, we know that. Now, take this example. Now, there are two examples. The first one is say number of member is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18, 19. Number of member is 19. Number of reactions are 3. So, total unknown is 22. M plus R and the number of joints 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, number of joints is J is equal to 10. Number of member is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, please correct it. This is 18. This is 18. So, this is 21, right. So, number of equations available is 2j, which is equal to 20. So, indeterminacy is say Ks, static indeterminacy is 21 minus 1, this is static indeterminacy. Now, consider the same example once again, but here this member is removed and this roller support is now replaced by a hinge support. Now, in this case what happens? In this case your number of member now becomes 17 and number of reactions are 4, 2 here and 2 here. So, total becomes 21 and number of joints is again same 5. So, number of joints is 10. So, your 2j is equal to 20. So, static indeterminacy is 1. Now, try to understand the difference between these two example. This is also indeterminate, this is also indeterminate. This is indeterminate because here the number of supports are additional support, extra support is provided. If we make this support roller, then this structure becomes determinate. But in this case, if we make this support roller, the structure will not become determinate, rather the structure will become unstable, because in this case this entire assembly can move in this direction. So, here just making by changing the support, by reducing the support constant, we cannot make the structure determinate, right. Here the indeterminacy is due to the additional member. So, if we remove one member, then the structure becomes determinate. If we remove one member, the M becomes 16 and then M is less than M becomes 17 and number of reaction is 3, total unknown is 20. So, in this case it is indeterminate because the additional internal force you have to compute, and in this case it is indeterminate because of additional support reaction we have to consider, we have to compute. So, in this case it is external and in this case it is internal indeterminacy. Okay. Now, these are some example of calculating static indeterminacy. Now, as I said, when we say that this is stable, we cannot take this condition for granted. It is just the necessary condition, but may not be the sufficient. There are some examples which I am going to show you in next 2 slides, where your structure is still statically determinate, structure is statically determinate and indeterminate. determinate, but the structure is not stable. Okay, we will see that now. Next example, next slide. For instance, you consider this example. Now, you see here number of, this is a statically determinate truss. As far as these equations are concerned, it is statically determinate truss. Now, in this truss, if you apply a load like this, then the structure may deform like this. So, entire assembly may collapse like this. So, the structure is statically determinate, but again not stable, right. Similarly, if we take another example, next example, it is again your it is m plus r greater than 2j. So, as far as the previous definition was concerned, this is indeterminate and stable, but again if you have apply a load like this, the structure, the entire assembly may collapse like this. In this case, the structure is indeterminate, this m plus r greater than 2j, but still the structure is unstable. So, as far as the stability of a structure is concerned, please do not take this equation for granted. It is just a necessary condition, but not the sufficient. Okay. So, this was the static indeterminacy. Now, quickly review what is kinematic indeterminacy. Now, if you already know the definition of degrees of freedom, the degrees of freedom of mechanical system is the number of independent coordinates required to completely specify the configuration of the system. In 2 dimension, we have, for any object in 2 dimension, we have 3 degrees of freedom, 2 translation and 1 rotation. We have seen this in the last class, right. Now, the kinematic, before we define kinematic indeterminacy, let us see what happens when you take a structure and apply load on the structure. When a structure is loaded, then the joints undergoes displacement, right, and in the form of translation and the rotation. And now, for instance, if we take a truss like this, and if it is subjected to some kind of load, the entire truss may deform like this. So, in this case, what happens? The point B goes here, it first goes here and then goes here in the form of translation. Point C goes here, and the D is a support, it remains same, and point D, what happens? Point D goes here and then goes here. So, every joints in a spherical tractor, they move from their original configuration, which has freedom to move from the original configuration in the form of translation and rotation. Okay. In rotation, you do not have here in the truss, because only translation degrees of freedom we have in a truss member. Now, the kinematic indeterminacy, for instance, for a beam, these are the rotations. These are the rotations. This is the rotation, right, for a beam, and for a truss also, for a frame also, this point goes here and this point rotate like this point, depending on the support condition and the constraint you have, right. Now, the kinematic indeterminacy is defined as, for a skeletal structure, the indeterminacy is the total number of degrees of freedom at various joints. Just to give you an example, what does it mean? This is the example just now we saw. Now, point A is fixed here. So, point A is hinged here. So, point A cannot move, only point B goes to B dash, point C goes to C dash, and point D goes to D dash. Now, let us see what are the possible, how this entire assembly from A, B, C, D to A dash, B dash, C dash and D dash, how these 2 configurations, the deformed configurations form from the original configuration. Now, what happens? You see, these are the different displacement. These are different displacement. These are horizontal displacement, horizontal and vertical displacement. Now, then how many displacement we have here is, we have 1, then 2, then 3, and 4, and then 5. So, total 5 joints movement has taken place, right. Now, the indeterminacy of this structure, the kinematic indeterminacy of this structure is then 5, right. Now, Takes few more example. For instance, in this case, all the joints are hinged here. So all these joints cannot move in space. All the joints, none of the joints have any degrees of freedom. So in this case, the total number of joint movements has taken place in this structure is 0. So in this case, the kinematic indeterminacy is 0, right? Now quickly see the another example. So nk is 0. So now for instance, in this case we have a simply supported beam and the blue one is the deformed configuration, and then you see these are the possible deformation given. The animation shows how the point A, B and B they can move in space. You see point A is hinge support. So only degrees of freedom this point A has is rotation. So point A can rotate, and point B has roller support. So it has 2 degrees of freedom. One is rotation like this, and another one is because of this roller, translation in this direction is also allowed. So this is another degrees of freedom that point B has. So then in this structure, the total degrees of freedom, 1 degrees of freedom is theta A, which is the rotation at A, and then theta B, rotation at B, and then translation at B. So total degrees of freedom, total joints movement we have is nk is equal to 3. So kinematic indeterminacy for this structure is 3. Now if we restrict this, if we make this structure, suppose, so in this case these are the 3 degrees of freedom. Now if we assume that the axial deformation of this member is neglected. Why this axial deformation takes place in this case? Point A is fixed in space, and then means it cannot move, no translation takes place at point A, but point A can move in this way, point B can move in this way. So there is a stretching takes place in member AB. So the member AB, the length of a member AB changes. But if we assume the length remains same, means there is no axial deformation allowed in member AB, then this is not allowed. So these degrees of freedom we do not have. So these degrees of freedom we do not have. So only degrees of freedom we have is theta A and theta B. So in this case, the kinematic indeterminacy of this structure is 2, right. So you see, now we stop here today. What we have done or reviewed here is what is static and kinematic indeterminacy, how for different structures static and kinematic indeterminacy can be determined. Okay. Now once we know what is determinate structure, indeterminate structure, and how to quantify indeterminacy, the next thing we need to understand is that what is static and kinematic admissibility and compatibility. Now we will review this static and kinematic admissibility and compatibility in the next lecture. Okay, we stop here today. Now see you in the next lecture.